Hello, we are back. We're gonna keep learning attention. Taking a bit longer time to implement attention or learning the fundamentals before diving into it. But I found this really good um, video by this guy Jamil, and I really like his presentations actually. So, um, so this guy Umar Jamil, like this is I think this guy is like diagrams are really nice, and I actually really like the font. And so I watched the dot product video, and I think one thing that's really good with his explanations is he um, helps us visualize sort of like the dimensions, um, because like I think when like I think like maybe I should
numbers, okay, like this. Imagine you have 512.
like 6 5 12. Like I think having those numbers, vocabulary size, like I don't know.
Of them along this road, 512 keys. The dot product of the first of the triple L with these words, all 105 paper.
Yeah, like these visualizations are really nice. But I think I do that too, right? And so each of these, like I actually like these. I think this is a little bit confusing. It's like, what are these? You know, like maybe if you, I don't know. I just don't want to be drawing these freaking horizontal lines. Does this make sense? put it here. You only need 3. Like, perhaps like the thing that you need to do is not necessarily just group these together actually. Group selection. Like perhaps what you need to do is, what if you like had it like this? Hmm. Is this bad visualization or is this? These. Like, I think the way I draw is a bit confusing. And then have it like this, and the sloppiness. To make it a bit easier to distinguish everything. I guess these two are equivalent. The way I'm representing this, in practice, this is the same as this. These spaces don't actually exist. It's just for visualization purposes. So we start from an input, we have a text, we tokenize it, byte pair encoding, and this is some it's learned separate of the model, and after the tokenizer, after it goes to the tokenizer, we have these indices, these one hot encoded indices, and what will happen is we will use these indices into a giant lookup table that we'll call like an embedding matrix. So the idea is like we want to encode these numbers, these indices, into some higher level, or actually you can think of it as right now we have, let's say our vocab size is 100,000, right? You can imagine that the network can learn. You can have like a 100,000 by your context window size. Instead of it being by C, it could be by 100,000. But now it's like way high dimensional. The dimension will be way too high. So let's say it's 512 here. So C and vocab here. There, we're just gonna change. I think like the I guess this is fine, right? It's a matrix. I want this to be like more bold. Now we apply a batch norm. So we have applied our layer normalization, and now what we want is to apply the actual attention mechanism.
Ideas never change because our vocabulary speaks.
Yeah, okay. I'll give credits to this guy for shit. You know, making good visualization is actually so hard. Because I also thought on group, maybe what we can do is see. You can make this less opaque. And now it's less jarring, right? Now it's a lot less jarring. The rows are a lot less jarring. Like ungroup selection. See like this is jarring. This is jarring to the eyes. Now this, set it to 50% opacity and you're good. It's about the attention to detail, my guy. Right? It's not about... You know, these things matter. How you present. Are we finally good? Okay. Think so. Alright, this is a minor cleanup, but it's now less jarring to the eyes. It's at, you know, less opacity. Okay, 50% opacity. So, I mean, this is good, but this is an abstraction, right? Like, how do we go from this index to the embedding?
But the embedding will change along with the training process of the model. So the embedding numbers will change according to the needs of the loss function. So the input embedding are basically mapping our single word into an embedding of size 500 grams. And with this quantity, 500 grams, each model, because it's the same name that is also used in the paper. Attention is all you need. Let's look at the next layer of the encoding, which is the positional encoding. So what is positional encoding? What we want is that each word should carry some information about its position in the sentence. Because
Yeah, these diagrams are really good.
Of words that are embeddings, but they don't convey any information about where that particular word is inside the sentence. And this is the job of the positional encoding.
The position encoding was stored.
First convert into embeddings using the previous layer, so the input embeddings, and these are embeddings of size 512. Then we create some special vectors called the positional encoding vector that we add to this embedding. So this vector we see here in the red is a vector of size 512, which is not learned. It's computed once and not learned along with the training.
And he...
And this word, so the first dimension with the first dimension, the second dimension with that, so we will get a new vector of the same size of the input vectors. How are these position embedding calculated? Let's see. Imagine we have a smaller sentence, let's say your cat is, and you may have seen the following expressions from the paper. What we do is we create a vector of size d model, so 512, and for each position in this vector, we calculate the value using these two expressions.
I think like these arrows, how about, I think we should keep it in the same row. This we apply layer normalization. Actually, I like it before, like, down. Are you good?
Using these arguments. So the first argument indicates the position of the word inside of the sentence. So the word your occupies the position 0. And we use for the even dimension, so the 0, the 2, the 4, the 510, etc., we use the first expression, so the sign. And for the odd positions of this vector, we use the second expression. And we do this for all the words inside of the sentence. So this particular embedding is calculated PE of 10 because it's the first word embedding 0. So this 1 represents the argument pos, and this 0 represents the argument 2i. And PE of 1, 1 means that the first word dimension 1. So we will use the cosine, giving the position 1, and the 2i will be equal to 2i plus 1 will be equal to 1. And we do this for the third word, etc. If we have another sentence, we will not have different positional encodings. We will have the same vectors, even for different sentences, because the positional encodings are computed once and reused for every sentence that our model will see during inference or training. So we only compute the positional encoding once. When we create the model, we save them, and then we reuse them. We don't need to compute it every time we feed the sentence to the model. So why the authors chose the cosine and the sine functions to represent positional encodings? Because let's watch the plot of these two functions. You can see the plot is by position, so the position of the word inside of the sentence, and this depth is the dimension along the vector, so the 2i that you saw before in the previous expressions. And if we plot them, we can see, as humans, a pattern here, and we hope that the model can also see this pattern. Okay, the next layer of the encoder is the multi-head attention. Save them. Why the authors chose the cosine and the sine functions to represent positional encoding? Because that's what the plot of these two functions. You can see the plot is by position, so the position of the word inside of the sentence, and this depth is the dimension along the vector, so the 2i that you saw before in the previous expressions. And if we plot them, we can see, as humans, a pattern here, and we hope that the model can also see this pattern. Okay, the next layer of the encoder is the multi-head attention. We will not go inside of the multi-head attention first. We will first visualize the single head attention, so the self-attention with a single head. And let's do it. So what is self-attention? Self-attention is a mechanism that existed before they introduced the transformer. The authors of the transformer just changed it into a multi-head attention. So how did the self-attention work?
I don't like how in this diagram it's not clear. How, like, if anything, like arguably this is a better visualization, and you can actually see what is happening, but I don't know, this was a bit confusing. Token embed, like these arrows don't tell me what's happening. Okay, so anyways.
Self-attention allows the model to relate words to each other. Okay, so we have the input embeddings that capture the meaning of the word. Then we have the positional encoding that gives the information about the position of the word inside of the sentence. Now we want this self-attention to relate words to each other. Now imagine we have an input sequence of 6 words with a D model of size 512, which can be represented as a matrix that we will call Q, K, and V. So our Q, K, and V is the same matrix representing the input. So the input of 6 words with the dimension of 512. So each word is represented by a vector of size 512. We basically apply this formula we saw here from the paper to calculate the attention, the self-attention in this case. Why self-attention? Because it's each word in the sentence related to other words in the same sentence. So it's self-attention. So we start with our Q matrix, which is the input sentence. So let's visualize it, for example. So we have 6 rows, and on the columns we have 512 columns. Now they are really difficult to draw, but let's say we have 512 columns, and here we have 6. Okay. Now what we do, according to this formula, we multiply it by the same sentence but transpose. So the transpose of the K, which is again the same input sequence, we divide it by the square root of 512, and then we apply the softmax. The output of this, as we saw before in the initial matrix notations, we saw that when we multiply 6 by 512 with another matrix that is 512 by 6, we obtain a new matrix that is 6 by 6. And each value in this matrix represents the dot product of the first row with the first column. This represents the dot product of the first row with the second column, etc. The values here are actually randomly generated, so don't concentrate on the values. What you should notice is that the softmax makes all these values in such a way that they sum up to 1. So this row, for example, here, sums up to 1. This other row also sums up to 1, etc., etc. And this value we see here is the dot product of the first word with the embedding of the word itself. This value here is the dot product of the embedding of the word your with the embedding of the word cat. And this value here is the dot product of the embedding of the word your with the embedding of the word is. The next thing, and this value represents somehow a score, that how intense is the relationship between one word and another. Let's go ahead with the formula. So for now, we just multiply Q by K divided by the square root of dk, apply to the softmax.
I really like this
so
one.
Let's go forward. We multiply this matrix by B, and we obtain a new matrix which is 6 by 512. So if we multiply a matrix that is 6 by 6 with another that is by the addition of the word is. The next thing.
Like, what's the dimension of this? Q. V. Yeah, so right before this. Yeah, I think this part is pretty confusing. Like, how do you get the attention matrix, right? And I gotta watch this video. Okay.
And this value represents somehow a scope.
So our input dimension, you have your context window size and then embedding dimension. After you apply this layer normalization and everything, and then what you want is you want a t by t, right?
Human by 500 words with 500 other words instead of let's say we have 500 columns, and here we have 6. Okay. Now what we do according to this formula, we multiply it by the same sentence by 512, and then we apply the softmax. The output of this, as we saw before in the initial matrix notations, we saw that when we multiply 6 by 512 with another matrix that is 512 by 6, we obtain a new matrix that is 6 by 6. And each value in this matrix represents the dot product of the first row with the first column. This represents the dot product of the first row with the second column, etc. The values here are actually randomly generated, so don't concentrate on the values. What you should notice is that the softmax makes all these values in such a way that they sum up to 1. So this row, for example, here, sums up to 1. This other row also sums up to 1, explicit, and this represents with the bit 12. So if you multiply a matrix that is 6 by 6,
Let's call this X. You have a T by C, a T. You want a T by C multiplied by a C by T to get a T by T This part.
Word with the embedding of the word itself. This value here is the dot product of the embedding of the word. The extension of this matrix is exactly the dimension, so let's say 6 rows with 512 columns, in which these are our words, so we have 6 words, and each word has an embedding of that so word, either in this case of notation. And so one has widths that are very distinguishable. By applying the formula special embedding for the values will not change, the position of the output will change. In each vector will not, it is learned by the model. I just took the initial sentence of, in this case, 6 words. We multiplied it by itself, we divide it by a fixed quantity, which is the square root of 512, and then we apply the softmax, which is not introducing any parameter. So for now, the self-attention rate doesn't require any parameter except for the embedding of the words. This will change later when we introduce the multi-head attention. Also, we expect, because each value in the self-attention, in the softmax matrix, is a dot product of the word embedding with itself and the other words, we expect the values along the diagonal to be the maximum, because it's the dot product of each word with itself. And there is another property of this matrix, that is, before we apply the softmax, if we replace the value in this matrix, suppose we don't want the word your and cat to interact with each other, or we don't want the word, let's say, is and the lovely to interact with each other, what we can do is, before we apply the softmax, we can replace this value with minus infinity, and also this value with minus infinity. And when we apply the softmax will replace minus infinity with 0. Because as you remember, the softmax is e to the power of x. If x is going to minus infinity, e to the power of minus infinity will become very, very close to 0. So basically 0. This is a desirable property that we will use in the decoder of the transformer. Now let's have a look at what is a multi-head attention. So what we just saw was the self-attention, and we want to convert it into a multi-head attention. You may have seen these expressions from the paper, but don't worry, I will explain them one by one. So let's go. Imagine we have our encoder, so we are on the encoder side of the transformer, and we have our input sentence, which is, let's say, 6 by 512, so 6 word by 512 is the size of the embedding of each word. In this case, I call it sequence by D model. So sequence is the sequence length, as you can.
And the transformer. So you're telling me that these guys decided to do CT when it should be TC?
See on the legend in the bottom shows where this, so what does the multi-head attention do? First of all, it multiplies these 3 matrices by 3 parameter matrices called WQ, WK, and WB. These matrices have dimension D model by D model. So if we multiply a matrix that is sequence by
This
D
is
model,
a great visualization.
D model by D model, we get a new matrix as output that is sequence by D model. So basically the same dimension as the starting matrix. And we will call them Q prime, K prime, and V prime. Our next step is to split these matrices into smaller matrices. Let's see how. We can split this matrix Q prime by the sequence dimension or by the D model dimension. In the multi-head attention, we always split by the D model dimension. So every head will see the full sentence, but a smaller part of the embedding of each word. So if we have an embedding of, let's say, 512, it will become smaller embeddings of 512 divided by 4. And we call this quantity dk. So dk is D model divided by h, where h is the number of heads. In our case, we have h equal to 4. We call this quantity, say, 5 dk. So dk is D, become a smaller part of the embedding of each word. So if we have an embedding of, let's say, 512, it will become smaller embeddings of 512 divided by 4. And we call this quantity dk. So dk is D model divided by h, where h is the number of heads. In our case, we have h equal to 4. We can calculate the attention between these smaller matrices, so Q1, K1, and V1, using the expressions taken from the paper. And this will result into a small matrix called head 1, head 2, head 3, and head 4. The dimension of head 1 up to head 4 is sequenced by dv. What is dv? It's basically it's equal to dk. It's just
Really?
dv because the
Is that how it works?
last multiplication is done by v, and in the paper they call it dv, so I'm also sticking to the same name. Our next step is to combine these matrices, these more heads, by concatenating them along the dv dimension, just like the paper says. So we concat all these heads together, and we get a new matrix that is sequenced by h multiplied by dv, where h multiplied by dv, as we know, dv is equal to dk, so h multiplied by dv is equal to d model. So we get back the initial shape. So it's sequenced by d model here. The next step is to multiply the result of this concatenation by wo. And wo is a matrix that is h multiplied by dv, so d model, with the other dimension being d model. And the result of this is a new matrix that is the result of the multi-head attention, which is sequenced by d model. So the multi-head attention, instead of calculating the
Damn,
attention,
watching this, like, I feel like my diagrams are not that great anymore. Like, it's actually fine to just use. Yes, this is great. QKT times V. If I seek, this is D model, like that's in the original paper. Yes, I'm confused about these dimensions.
Very briefly, so the multi-head attention has
Where's the
matrices here, so Q prime, K prime, and V prime, splits them along the D model dimension into smaller matrices and calculates the attention between these smaller matrices. So each
because
head
V is a different dimension.
different aspects of the embedding of each word. Why we want this? Because we want each head to watch different aspects of the same
Q is a different dimension.
language, but also another language. One word may be a noun in some cases, maybe a verb in some other cases, maybe an adverb in some other cases, depending on the context. So what we want is that one head maybe learns to relate that word as a noun, another head maybe learns to relate that word as a verb, and another head learns to relate that word as an adjective or a verb. So this is why we want multi-head attention. Now you may also have seen online that the attention can be visualized, and I will show you how. When we calculate the attention between the Q and the K matrices, so when we do this operation, so the softmax of Q multiplied by the K divided by the square root of dk, we get a new matrix just like we saw before, which is sequence by sequence, and this represents a score that represents the intensity of the relationship between the two words. We can visualize this, and this will produce a visualization similar to this one, which I took from the paper, in which we see how all the heads work. So for example, if we concentrate on this word making, this word here, we can see that making is related to the word difficult, so this word here, by different heads, so the blue head, the red head, and the green head. But the violet head is not relating these two words together, so making and difficult is not related by the violet or the pink head. The violet head or the pink head, they are relating the word making to other words, for example to this word 2009. Let's see, also wondering why these three matrices are called query keys and values. Okay, these terms come from the database terminology or from the Python-like dictionaries, but I would also like to give my interpretation of my own, making a very simple example. I think it's quite easy to keys are the category of movies, and the values are the movies belonging to that category. In my case, I just put one value. So we have romantic category, which includes Titanic. We have action movies that include The Dark Knight, etc. Imagine we also have a user that makes a query, and the query is love. Because we are in the transformer world, all these words actually are represented by embeddings of size 512. So what our transformer will do, he will convert this word love into an embedding of 512. All these queries and values are already embeddings of 512, and it will calculate the dot product between the query and all the keys, just like the formula. So as you remember, the formula is softmax of query multiplied by the transpose of the keys divided by the square root of the model. So we have
That's a good way to explain it.
with all the keys. In this case,
what do I contain?
One by one. And this will
what do I actually contain? What I'm looking for, what do I contain, and what I can contain, what can I looking for? I represent I think this interpretation is pretty good.
Values or not amplify other values. In this case, our embedding may be in such a way that the word love and romantic are related to each other. The word love and comedy are also related to each other, but not so intensively like the word love and romantic, so its score in encoder is close to 0. Our next layer in the encoder is add and norm. And to introduce the add and norm, we need the layer normalization. So let's see what is the layer normalization. This and this section is the content normalization. We are carefully treating each item in the batch independently, which we have its own mean and its own. So the input embeddings in this case they are called output embeddings, but the underlying working is the same. Here also we have the positional encoding, and they are also the same as the encoder. The next layer is the masked multi-head attention, and we will see it now. We also have the multi-head attention here with the. Here we should see that there is the encoder here that produces the output and is sent to the decoder in the forms of keys and values. While the query, so this connection here is the query coming from the decoder. So in this multi-head attention, it's not a self-attention anymore, it's a cross-attention because we are taking two sentences. One is sent from the encoder side, so let's write encoder. The attention put feed to this multi having the feed for earlier, which we will see later. So let's have a look at the masked multi-head attention and how it differs from a normal multi-head attention. What we want, our goal is that we want to make the model causal. It means that the output at a certain position can only depend on the words on the previous position. So the model must not be able to see future words. How can we achieve that? As you saw, the output of the softmax in the attention calculation formula is this matrix sequence by sequence. If we want to hide the interaction of some words with other words, we delete this value and we replace it with minus infinity before we apply the softmax, so that the softmax will replace this value with 0. And we do this for all the interaction that we don't want. So we don't want your to watch future words. So we don't want your to watch cat is a lovely cat. And we don't want the word cat to watch future words, but only all the words that come before it or the word itself. So we don't want this. Also the same for the other words, etc. So we can see that we are replacing all the words, all these values here that are above this diagonal here. So this is so that the top can be calculated based on this view. Let's see in which stage of the multi-head attention this mechanism is introduced. So when we calculate the attention between these molar matrices, so Q1, K1, and B1, before we apply the softmax, we replace these values. So this one, values into zeros. So basically, the model will sum up to without any information from this interaction. So it's like this word cannot interact. Now we will be dealing with the translation task. So from many, it's easy to visualize. I love you very much. Easy to understand all the steps. Let's start with the easy to model and with scribe. Let's go. We start with description of the these two tokens are taken from the vocabulary. So they are special tokens in our vocabulary. See, from the picture, we take our recorder input sequence. So as I saw, we saw previously, embedding the input, embedding three words with two words in the sentence with order. Here you can see shifted right. What does it mean to shift right? Basically, it means we prepare a special token called SOS, start of sentence. You should also notice that these two sequences actually, when we code the transformer, so if you watch my other video on how to code the transformer, you will see that we make this sequence of fixed length, so that if we have a sentence that is Tiamomoto or a very long sequence, actually when we feed them to the transformer, they all become of the same length. How to do this? We add padding words to reach the length, the desired length. So if our model can support, let's say, a sequence length of 1000, in this case we have a 4 tokens, we will add 996 tokens of padding to make this sentence long enough to reach the sequence length. Of course, I'm not doing it here because it's not easy to visualize. Okay, we prepare this input for the decoder. We transform into embeddings. We add the positional encoding. Then we send it first to the multi-head attention, to the masked multi-head attention, so along with the causal mask. And then we take the output of the encoder and we send it to the decoder as keys and values, while the queries are coming from the masked. So the queries are coming from this layer, and the keys and the values are the output of the encoder. The output of all this block here, so all this big block here, will be a matrix that is sequenced by D model, just like for the encoder. However, we can see that this is still an embedding because it's a D model, it's a vector of size 512. How can we relate this embedding back into our dictionary? How can we understand what is this word in our vocabulary? That's why we need a linear layer that will map sequence by D model into another sequence by vocabulary size. So it will tell for every embedding that it sees what is the position of that word in our vocabulary, so that we can understand what is the actual token that is output by the model. After that, we apply the softmax. And then we have our label, what we expect the model to output given this English sentence. We expect the model to output this, Tiamomoto end of sentence. And this is called the label or the target. What we do when we have the output of the model and the corresponding label, we calculate the loss. In this case, it's the cross entropy loss, the EOS. So it's 4 CD. It will say that with recurrent neural networks, we have n time steps to map n specific frequency. Let's have a look at how inference works. So, end of sentence. And output, which is other words. What we do is, for the decoder, we give him just the start of sentence, and of course we add enough padding tokens to reach our sequence length. We just give the model the start of sentence filter as back to give this for the transformer mod. When we inference, however, we need to do it token by token, and we will also see why this is the case. Our English sentence didn't change, so we hope the encoder should, as T, we append it to the input of the output is AMO. English sentence didn't put of the T. We will solve the translation model. There are many strategies for inferencing. What we use is called greedy strategy. So for every step, we get the word with the maximum softmax value. And however, this strategy works. Usually not bad, but there are better strategies. And one of them is called beam search. In beam search, instead of always greedily, so this is that's why it's called greedy. Instead of greedily taking the maximum top value, we take the top B value.
Boy, my phone is, my computer is so slow.
We infer what are the next possible tokens for each of the top B values at every step, and we keep only the one with the most probable sequences, and we delete the others. This is called beam search, and generally performs better. So thank you guys for watching. I know it was a long video, but it
This is a great video. Good job. Alright, llama.
basically means that we have an input sequence and the prompt. So for example, if we tell him poem, for example, without the last word, probably it will come up with the last word that is missing from that poem. In this case, I will be using one very famous passage from that first alert. How does the training work? Well, we give the input is bit to the second token of will produce second token as output, so love that. And if we give the first 3 tokens, it will produce the output, the third token as output. Of course, the model will also produce the output for the previous 2 tokens. But let's see the inference. So, if you remember from my previous videos in which I do the inferencing, when we train the model, we only do it in one step. So we give the input, we give the target, we calculate the loss, and we don't have any for loop to train the model for one single sentence. But for the inference, we need to do it token by token. So in the inference, we start with the time step, time step 1, in which we only give the input SOS, so start of sentence, and the output is love. Then we take the output token here, love, and we append it to the input, and we give it again to the model, and the model will produce the next token, love that. Then we take the last token output by the model, that, we append it again inside. Then the description, what I mean by this is that to output, for example, the word D, the model has to see all the input here. We cannot just give the C's. The model needs to see all the input to output this last output. And that we already, this is what we do with the KV cache. So the KV cache is a way to do less computation on the tokens that we have already seen during inferencing. So it's only applied during inferencing in a transformer model. And it not only applies to the transformer of like the one in Llama, but to all transformer models, because all transformer models work in this way. This is a description, it's a picture of how the self-attention works during the next token prediction task. So, as you saw also in my previous slides, we have a query matrix here with n tokens. Then we have the transpose of the keys. So the query can be thought as rows of vectors, where the first vector represents the first token, the second token, etc. Then the transpose of the keys is the same tokens but transpose, so the rows become columns. This produces a matrix that is n by n. So if the initial input matrix is 9, the output matrix will be 9 by 9. Then we multiply it by the V matrix, and this will produce the attention. The attention is then fed to the linear layer of the transformer. Then the linear layer will produce the logits, and the logits are fed to the softmax, and the softmax allow us to decide which is the token from our vocabulary. Again, if you're not familiar with this, please watch my previous video of the transformer about the inferencing of the transformer, and you will see this clearly. So this is a description of what happens at the general level in the self-attention. Now let's watch it step by step. So imagine at the inference step 1, we only have the first token. If you remember before, we were only using the start of sentence token. So we take the start of sentence token, we multiply it by itself, so transpose it. It will produce a matrix that is 1 by 1. So this matrix is 1 by 4096, multiplied by another matrix that is 4096 by 1. It will produce a 1 by 1 matrix. Why 4096? Because the embedding vector in Llama is 4096. Then the output, so this 1 by 1 is multiplied by the B, and it will produce the output token here. And this will be our first token of the output. And then we take the output token, this one, and we append it to the input at the next step. So now we have two tokens as input. They are multiplied by itself, but with a transposed version of itself, and it will produce a 2 by 2 matrix, which is then multiplied by the V matrix, and it will produce two output tokens. But we are only interested in the last tokens output by the model, so this one, attention 2, which is then appended to the input matrix at the time step 3. So now we have 3 tokens in the time step 3, which are multiplied by the transposed version of itself, and it will produce a 3 by 3 matrix, which is then multiplied by the V matrix, and we have this 3 tokens as output. But we are only interested in the last token output by the model, so we append it again as input to the Q matrix, which is now 4 tokens, which is multiplied by the transposed version of itself, and it will produce a 4 by 4 matrix as output, which is then multiplied by this matrix here, and it will produce this attention matrix here. But we are only interested in the last attention, which will be then added again to the input of the next step. But we notice already something. First of all, we already here in this matrix where we compute the dot product between this token and this token and this token and this. So this matrix is all the dot products between these two matrices. We can see something. The first thing is that we already computed these dot products in the previous step.
We're in Q and K, so why?
As you can see, this matrix is growing.
Why are we not caching Q as well?
See, there is a lot of attention because we are every time we are inferencing the transformer, we are giving him.
Why is not the QKV cache?
Recomputing all these dot products, which is inconvenient because we actually already computed them in the previous time step. So is there a way to not compute them again? Can we kind of cache them? Yes, we can. And then, since the model is causal, we don't care about the attention of a token with its successors, but only with the token before it. So, as you remember, in the self-attention, we apply a mask, right? So the mask is basically, we don't want the dot product of one word with the word that come after it, but only the one that comes before it. So basically, we don't want all the numbers above the principal diagonal of this matrix. And that's why we applied the mask in the self-attention. But okay, the point is we don't need to compute all these dot products. The only dot products that we are interested in is this last row. So because we added the token 4 as input compared to the last time step, so we only have this new token 4, and we want this token 4. How
we don't need to cache the previous ones.
So basically, we are only interested in this last row here. And also, as we only care about the attention of the last token, because we want to select the word from the vocabulary, so we only care about the last row. We don't care about producing these 3 attention scores here in the output sequence of the self-attention. We only care about the last one. So is there a way to remove all these redundant calculations? Yes, we can do it with the KV cache. Let's see how. So With the KV cache, basically, what we do is we cache the query, so sorry, the keys and the values, and every time we have a new token, we append it to the key and the values, while the query is only the output of the previous step. So at the beginning, we don't have any output from the previous step, so we only use the first token. So the time step one of the inference is the same as without the cache. So we have the token one with itself, we produce a matrix one by one, multiplied with one token, and we produce one attention. However, at the time step two, we don't append it to the previous query. We just replace the previous token with the new token we have here. However, we keep the cache of the keys, so we keep the previous token in the keys, and we append the last output to the keys here, and also to the values. And if you do this multiplication, it will produce a matrix that is 1 by 2, where the first item is the dot product of the token 2 with the token 1, and the token 2 with the token 2. This is actually what we want. And if we then multiply with the V matrix, it will only produce one attention score, which is exactly the one we want. And we do again, so we take this attention 2, and this will become the input of the next inference step, so this token 3. We append it to the previously cached K matrix and also to the previously cached V matrix. This multiplication will produce an output matrix that we can see here. The multiplication of this output matrix with this V matrix will produce one token in the output, which is this one, and we know which token to select using this one. Then we use it as an input for the next inferencing step by appending it to the cached keys and appending to the cached V matrix. We do this multiplication and we will get this matrix, which is 1 by 4, which is the dot product of the token 4 with the token 1, the token 4 with the token 2, token 4 with the token 3, and the token 4 with itself. We multiply by the V matrix, and this will only produce one attention, which is exactly what we want to select the output token. This is the reason why it's called the KV cache, because we are keeping a cache of the keys and the values. As you can see, the KV cache allows us to save a lot of computation because we are not doing a lot of dot products that we used to do before. And this makes the inferencing faster. The next layer that we will be talking about is the group multiquery attention. But before we talk about the group multiquery attention, we need to introduce its predecessor, the multiquery attention. Let's see. So let's start with the problem. The problem is that the GPUs are too fast. If you watch this datasheet, this is from the A1 GPU from NVIDIA, we can see that the GPU is very fast at computing and performing calculations, but not so fast at transferring data from its memory. That means, for example, that the bytes per second is nearly 10 times slow, and this means that sometimes the bottleneck is not how many, it's 10 times now of the attention paper, so attention is all you need. And in this paper, he introduced the problem. He said, well, attention paper, so attention is all you need. And in this paper, he introduced the problem. He said, well, let's look at the multi-head attention, so the batched multi-head attention. This is the multi-head attention as presented in the original paper, attention is all you need. Let's look at the algorithm and let's calculate the number of arithmetic operations performed and also the total memory involved in these operations. So he calculated that the number of arithmetic operations is performed in O1, O of B and D squared, where B is the batch size, N is the sequence length, and D is the size of the embedding vector. While the total memory involved in the is given by the sum of all the tensors involved in the calculations, including the derived ones, is equal to O of B and D plus B. To compute the rate number K that we perform is much less than the number that, and then the KV cache we created. I mean, not a new problem, but we actually we have a new bottleneck, and it's not the computation anymore. So this algorithm here is the multi-head self-attention, but using the KV cache. And this reduces the number of operations performed. So if we look at the number of arithmetic operations performed, it's B and D squared. The total memory involved in the operations is B n squared D plus N D squared. And the ratio between the two is this, O of N divided by D plus 1 divided by D. So the ratio between the total memory and the number of arithmetic operations. This means that when N is very similar to D, this ratio will become 1. Or when D is very similar to 1, or in the limit of 1, so the batch size is 1, this ratio will become 1. And this is a problem because now, when this condition is verified, it's true, then the memory access becomes the bottleneck of the algorithm. And this also means that either we keep the dimension of the embedding vector much bigger than the sequence length, but if we increase the sequence length without making the dimension of the embedding vector much bigger, the memory access will become the bottleneck. So what we can do is we need to find a better way. To solve the problem of the previous algorithm in which the memory became the bottleneck, we introduced a multi-query attention. So what the author did was to remove the h dimension from the k and the b, while keeping it for the q. So it's still a multi-head attention, but only with respect to q. That's why it's called a multi-query attention. So we will have multiple heads only for the q, but the k and b will be shared by all the heads. And if we use this algorithm...
Okay, I'm zoning out.
So the Zwickau function was analyzed in this famous paper from Noam Chazir, who is also one of the authors of the attention model, who is also one of the author of the multi-query attention that we saw before. So let's have a look at this paper. So the author compared the performance of the transformer model by using different activation functions in the feed-forward layer of the transformer architecture. And the one we are interested in is this Zwickau here, which is basically the Swiss slower to transferring data than it is at
with the installation of Dynamo will be enabled. Constructed a multi-client multi-round workload, which was of course each client will send a new ISL to the server, and if usage is almost like 100%. So which means many KB cache will be executed. That's where our solution kicks in. And we can see the Dynamo KB manager log.
We did various quantitative. This is very weak. We also support serving models with multiple LoRa adapters, which can be dynamically located that real feet. Then you might want to write custom kernels for instance. For example, launch with CUDA graph to minimize the host overhead. Another critical factor in performance is how the entire system is architected. During the development of VLM, we believe that successfully talk about how we also host regular meetups and open. PyTorch has been a key part of our sustainability and LD, and pure FLM is typically everything from scratch. Which still offers so much while we are currently in the middle of the process. Okay, let's go over it one by one. The very first way we integrated Torch.compile was to apply it locally, therefore this more broader in a way that relation. So this actually involves some exciting possibilities like adding custom, making this possible. We truly believe these hardware backends are promising and
instancy model pairs, such as like Llama 68M model to speculate a Llama 270 model, 70 model to speculate a 70B model. You will check the key in the lookup table. Blue bar shows the latency of the speculative coding, the single byte dynamic, and we are actively working on the DSD's integration into VLM to make speculative coding always beneficial for serving. Lastly, I want to briefly mention how to use speculative coding in VLM. It's actually very simple. So when you launch the server, you can specify the draft model you want to use and the number of tokens you want to speculate. Here, we also specify that we use a different tensor parallel size for the draft model because it's small and more efficient to run on a single GPU. For n-gram-based model, you just change the name of speculative model to n-gram.
Don't know what she's saying.
As the user is typing, you can have, you're probably going to use some piece of context, and you can know that before the user's done typing. So, as we discussed before, reusing the KB cache results in lower latency, lower cost across requests. So as the user starts typing, you can immediately warm the cache with, like, let's say the current file content. And then when they press enter, there's very few tokens it actually has to pre-fill in the queue before starting the generation. This will significantly lower TTFD.
Can you explain how KB cache works?
Yeah. So the way transformers work.
I like it.
One of the mechanisms that allow transformers to not just independently, like the mechanism that allows transformers to not just independently look at each token, but see previous tokens, are the keys and values to attention. And generally the way attention works is you have at your current token some query, and then you've all the keys and values of all your previous tokens, which are some kind of representation that the model stores internally of all the previous tokens in the prompt. And like by default, when you're doing a chat, the model has to, for every single token, do this forward pass through the entire model. That's a lot of matrix multiplies that happen, and that is really, really slow. Instead, if you have already done that and you stored the keys and values and you keep that in the GPU, then when let's say I have stored it for the last n tokens, if I now want to compute the output token for the n+1 token, I don't need to pass those first n tokens through the entire model because
Wow. UL.
already have all those keys and values. And so you just need to do the forward pass through that last token. And then when you're doing attention, you're reusing those keys and values that have been computed, which is the only kind of sequential part, or sequentially dependent part of the transformer.
Is there like higher level caching, like caching of the prompts or that kind of stuff?
I
that
see.
can help?
Yeah, there's other types of caching you can kind of do. One interesting thing that you can do for Cursor Tab is you can basically predict ahead as if the user would have accepted the suggestion and then trigger another request. And so then you've done speculative, it's a mix of speculation and caching, right? Because you're speculating what would happen if they accepted it. And then you have this value that is cached, this suggestion. And then when they press tab, the next one would be waiting for them immediately. It's a kind of clever heuristic / trick that uses a higher level caching and can give it feels fast despite there not actually being any changes in the model.
And if you can make the KV cache smaller, one of the advantages you get is like maybe you can speculate even more. Maybe you can guess here's the 10 things that could be useful. Like you predict the next 10, and then like it's possible the user hits the one of the 10. It's like much higher chance than the user hits like the exact one that you show them. Maybe they type another character in, and we sort of hit something else in the cache.
Yeah.
So there's all these tricks where the general phenomena here is I think it's also super useful for RL is maybe a single sample from the model isn't very good, but if you predict like 10 different things, it turns out that one of the 10 that's right is the probability is much higher. So there's these passive K curves, and part of RL like what RL does is you can exploit this passive K phenomena to make many different predictions, and one way to think about this, the model sort of knows internally has some uncertainty over like which of the key things is correct, or like which of the
So
key
yes,
things is
this guy knows his stuff. No, it's not. Who was the guy explaining this? He's really good.
with the RL or Cursor Tab model, one of the things we're doing is we're predicting which of the 100 different suggestions the model produces is more amenable for humans, like which of them do humans more like than other things. Maybe like there's something where the model can predict very far ahead versus like a little bit, and maybe somewhere in the middle, and then you can give a reward to the things that humans would like more, and sort of punish the things they would like, and sort of then train the model to output the suggestions that humans would like more. You have these like RL loops that are very useful to exploit these passive K curves. Oman maybe can go into even more detail.
Yeah, it is a little different than speed, but I mean, like technically you tie it back in because you can get away with a smaller model if you RL your smaller model and gets the same performance as the bigger one. like, and Swally was mentioning stuff about about reducing the size of your KD cache. There are other techniques there as well. They're really helpful for speed. So kind of back in the day, like all the way 2 years ago, people mainly use multi-head attention. And I think there's been a migration towards more efficient attention schemes like group query or multi-query attention. And this is really helpful for then, with larger batch sizes, being able to generate the tokens much faster. The interesting thing here is this now has no effect on that time to first token pre-bill speed. The thing this matters for is now generating tokens. And why is that? Because when you're generating tokens, instead of being bottlenecked by doing these super parallelizable matrix multiplies across all your tokens, you're bottlenecked by how quickly, it's for long context with large batch sizes, by how quickly you can read those cache keys and values. And so then that's memory bandwidth, and how can we make this faster? We can try to compress the size of these keys and values. So multi-query attention is the most aggressive of these, where normally with multi-head attention, you have some number of quote-unquote attention heads, and some number of query heads. Multi-query just preserves the query heads, gets rid of all the key value heads. So there's only one kind of key value head, and there's all the remaining query heads. With group query, you instead preserve all the query heads, and then your keys and values are kind of, there are fewer heads than keys and values, but you're not reducing it to just one. But anyways, like the whole point here is you're just reducing the size of your KD cache.
And then there is MLA.
Yeah, multi-latent. That's a little more complicated, and the way that this works is it kind of turns the entirety of your keys and values across all your heads into this kind of one latent vector that is then kind of expanded inference time.
But MLA is from this company called DeepSeek. It's quite an interesting algorithm. Maybe the key idea is sort of in both MQA and in other places, what you're doing is sort of reducing the the number of KV heads. The advantage you get from that is there's less of them, but maybe the theory is that you actually want a lot of different. If you want each of the keys and values to actually be different, so one way to reduce the size is you keep one big shared vector for all the keys and values, and then you have smaller vectors for every single token, so that when you can store only the smaller thing. There's some sort of like low rank reduction, and the low rank reduction will and at the end of the time when you eventually want to compute the final thing, remember that like your memory bank, which means that like you still have some simple compute left that you can use for these things. If you can expand the latent vector back out, and somehow like this is far more efficient because just like you're reducing like for example maybe like reducing like 32 or something like the size of the vector that you're keeping.
Yeah, there's perhaps some richness in having a separate set of keys and values and query that kind of pairwise match up versus compressing it all into one. In that interaction, at least.
Okay, and all of that is dealing with being memory bound.
Yeah.
And ultimately, how does that map to the user experience? Trying to give them.
Yeah, the two things that maps to is you can now make your cache a lot larger because you've less space allocated to the KD cache. You can make cache a lot more aggressively and a lot more things. So you get more cache hits, which are helpful for reducing without degrading.
We want there to be options, right? The backside stuff happening in the background, and we're experimenting with a lot of things. Right now, we don't have much of that happening, other than like the cache warming or like figuring out the right context that goes into your command prompts, for example. But the idea is if you can actually spend computation in the background, then you can help the user maybe like at a slightly longer time horizon than just predicting the next few lines you're going to make, but actually like in the next 10 minutes what you're going to make. And by doing it in the background, you can spend more computation doing that. And so the idea of the shadow workspace that we implemented, and we use it internally for like experiments, is that to actually get advantage of doing stuff in the background, you want some kind of feedback signal to give back to the model, because otherwise, like you can get higher performance by just letting the model think for longer, and so like one is a good example of that. But another way you can improve performance is by letting the model iterate and get feedback. And so one very important piece of feedback when you're a programmer is the language server, which is this thing. It exists for most different languages, and there's like a separate language server per language, and it can tell you you're using the wrong type here, and it gives you an error, or it can allow you to go to definitions or understands the structure of your code. So language servers are extensions developed by like there's a TypeScript language server developed by the TypeScript people, a Rust language server developed by the Rust people, and then they all interface over the language server protocol to VS Code. So that VS Code doesn't need to have all of the different languages built into VS Code, but rather you can use the existing compiler infrastructure.
For linting purposes?
It's for linting, it's for going to definition, and for like seeing the right types that you're using.
So it's doing type checking also?
Yes, type checking and going to references. And that's like when you're working on a big project, you kind of need that. If you don't have that, it's like really hard to code in a big project.
Can you say again how that's being used inside Cursor, the language server protocol communication thing?
So it's being used in Cursor to show to the programmer just like in VS Code. But
and then instead of you operating in ground truth version of the files.
The query is sort of like what I'm looking for. Key is sort of like what can I potentially contain. And value is actually the actual value. And so the query will be used at runtime to figure out, okay, what are the words that I should be looking at that are important. And the value will tell you, okay, the keys will tell you sort of like, okay, this is sort of like what this word will represent, and then once you have a key and a query and key match, that will tell you the importance of the actual value. How much should you, that dot product will tell you how much you should be paying attention for that particular value of that word or that token, that embedding. The model is initially B, I guess BTC. That's your batch. Channels where C is the embedding dimension. And then we'll have W. I thought like think like in the original model, it's like that too, right? So sequence and length. So that was what the guy was explaining when he was doing transformer QKV. What?
Hello, everyone, and welcome to another episode. Now, jumping into next, let's talk.
I think the other guy explains it better.
Alright, welcome to my video about the transformer. And this is actually the version 2.0 of my series on the transformer. I had a previous video in which I talked about the transformer, but the audio quality was not good, and as suggested by my before, we have to print half for the and replace this fat. And we do this also the same for the other the formula is the soft. We don't just query coming from the edit this matrices in this matrix. This is fast so mix it together. So making a difficult this work that it out there it has eating some check head. The other that is yet to feed new matrix that is
This other guy was saying
transform within these three are not, and since there is only vector represents the new token in this decoder step, and since there is only one segment, this is a vector instead of a matrix. The key matrix represents all the matrix product about and all of the time space quadrant. Obviously, this is road Italian matrix. Instead, it's in with the rest of the transformer.
and that do like this the current layers calculation for the matrices K and V that we need to store. Precision
Sequence.
is the number of bytes per parameter. For example, in FP32, there are 4 bytes
What's and layers
per parameter.
and vocab. I need to figure out like what's a good variable name. Called like somewhere. Group norm. Shape suffix. Variable name plus shape dimension. I think L is a better. I don't think T, like Karpathy used T, but T I think was confusing. Shazir goat.
Talk about some self-attention. In order to create an denominator, the square root of some dimension of q and k, well, this is...
So Q is going to be, you have your batch. Oh my god. Length and decay. I think D model. Oh, Q is going to be a result of D model is dk. But actually dk is equal to D model over number of heads, because you split it up and you split your embedding essentially into like different chunks, and so you compute that dot product dk times dk over your vocabulary size. Huh. How does that work? Because you split it up into these, but then this first chunk, dk, cannot talk to k2. Isn't multi-head bad? I am like, you are splitting up the embedded into multiple parts, and so the first, the embedding can never to the fifth. And the embedding heads to each. That's a great question, right? There's a tension with regards to but the problem is you only get the only has access to a lower dimension. What is the work that you're working on lower dimensional subspace specialization? Why the confusion? learn this stuff, man.
Sure.
Sequence length. I think this right here is terrible. It's nowhere to be found. Like, what does this even mean? Like, it's from here. Is it in the original paper? You know, anything that's not in the original paper, don't think I should look at. Oh well, where did it go?
Remote taking it, where h multiplied by dv, as we know, dv is equal to dk, so h multiplied by dv is equal to d model. So we get back the initial shape. So it's sequenced by result of this, that is denotation by wo, and wo is a matrix that is h multiplied by dv, so d model, multiply with the other dimension being d model. And the result of this is a new matrix that is the result of the multi-head attention, which is sequenced by D model. So the multi-head attention, instead of calculating the attention between these matrices here, so Q prime, K prime, and V prime, splits them along the D model dimension into smaller matrices and calculates the attention between these smaller matrices. So each head is watching the full sentence, but a different aspect of the embedding of each word. Why we want this? Because we want each head to watch different aspects of the same word.
We want each head to watch different aspects of the same word. Each head to watch.
Want each head to watch different aspects of the same word. For example, in the Chinese language, but also in other languages, one word may be a noun in some cases, may be a verb in So what we want is that one head maybe learns to relate that word as a noun, another head maybe learns to relate that word as a verb, and another head learns to relate that verb as an adjective or an adverb. So this is why we want multi-head.
N layers is the number of layers in a model, which now 8. If we multiply everything together, we get that the KV cache for this model is predicted when the MV matrices for every token in the prompt.
Let's say we only had a single head, right? In which case you would it be BCL? We want to model the relationship so it's the length by the in practice. So in practice, do is you actually want, like, how does this actually look like? It's like you would have actually you actually want like this is fun too. Like this is kind of what you want. Row times column. So actually this doesn't really make sense. Alright, so really what you want is a relationship what you want to do is this. Right, so it would just be like a sum between and the reason for that is that it's easier to, if it's owned by C, I just hate that it's Like the other way around, if you multiply these two matrices together, it doesn't really make sense, right? Because you're trying to figure out essentially, so like these two words, how related are they to each other? And if you matrix multiply this way, then you're doing a row. You end up with like a C by C, which would be I don't know, it'd just be weird. Like you actually like multiplying across features. For the same you're saying like across the features for this time, how related are they? Which doesn't really make sense. It's easier to visualize time like this than going down. So far we've been visualizing our embeddings as CL. Below will to generate a C by C matrix attention. We need to multiply LC CL. You could say like Q transpose. If it's CL, you need to do to stick to paper or I think I use WQ capital, right? It's all by C.
Recurrent neural nets. The difference pass this into the encoder
representing the relationships attention block. The next weight matrices WQ, WK, Z. So we will have multiple attention vectors Z for every word. However, our neural net is only expecting one attention vector per word. So we use another weighted matrix, WZ, to make sure that the output is still and attention we have larger. This smoothens out the loss surf. Typically we would apply a batch normalization. This smoothens out
All right, we're gonna keep going tomorrow.